Hi there, I'm here with Balloon Man. Oh, Balloon Man, you say the nicest things. We're going to be doing the practice problems for Module 3. Thanks, Balloon Man. Okay, so these are on page 98. And Balloon Man, will you squeak the first one for me? Actually, just read it in a normal voice. Sorry, Balloon Fellow.
Chemist uses an experiment similar to experiment 3.2 to decompose 150.0 grams of water, or H2O. If the chemist finds that he makes 16.7 grams of hydrogen from the decomposition, how much oxygen must he have produced?
Okay, so he has 150 grams of water, and
which is 2 parts hydrogen to 1 part oxygen.
And how much hydrogen does he measure?
16.7 grams.
Okay. So in order to solve this, we have to remember, can you make sure you don't shake your little, the law of mass conservation. And the law of mass conservation says that matter cannot be created or destroyed, only changed in form. So if we have the same amount of mass at the beginning, we should have the same amount of mass at the end. So how can we solve this? It's very easy. We're just going to do a subtraction because we're told that there's nothing left over, right? Or they don't tell us anything about leftover. What do they say about leftovers?
That's all.
Nothing.
Good.
Yeah. So we assume that there are no leftovers. So we're simply going to subtract 17.6 grams to get it. Okay. And we get 3. Okay, we got 133.3 grams. Is that how we should express our answer, Martin? What yes. Operation are we performing? We're performing subtraction, and so we want to worry about precision. Yes. These are both precise to the 10th place, so this is the precision we should have in our answer. We've got 133.3 grams. Number 2.
A compound is decomposed into its constituent elements of carbon, nitrogen, and hydrogen. If in the decomposition 12.0 grams of carbon, 14.0 grams of nitrogen, and 3.0 grams of hydrogen were formed, what was the mass of the compound before it was decomposed?
This is again using the law of mass conservation. Since we're adding, we're going to be precise to 10th, so we're going to keep our 0 in the decimal place. 29.0 grams. That's our answer. Okay.
3. Identify the following as metal or nonmetal. I, Y, N, R-E. Yeah, that's right.
Okay, so looking at the textbook, we can look at these. So I'll tell you, I happens to be number 53. Y happens to be number 39. N happens to be number 7, and RE is 75. If you look at the front of the textbook, you find the best list and list on the inside cover of the names. So number 53I is, look on the, I know what it is, but look in the table here and tell me what it is. I just want you to get the practice of looking it up in the table. So that's alphabetical, fortunately. So just look up the I.
Okay, let's see. I. That's iodine.
It is. What's Y? Number 39.
That's yttrium.
Yes, yttrium. Great name, huh? What's N?
That's nothing. There's ytterbium.
It's nitrogen. How about RE?
What? No, I was talking about the other one. That starts with Y.
Oh.
RE is. That's rhenium.
Rhenium. Yeah.
Yeah, that.
Okay, for the Rhine. So looking at the periodic table, just look here. Please tell me which of these are metals and which are non-metals.
Okay, so I is a non-metal.
Non-metal. Yttrium.
Metal.
Metal. Nitrogen.
That is a non-metal.
Non-metal. Rhenium. It's number 75.
Yeah, that's a metal.
Metal, good. Okay, moving on to number 4.
Aw, already wrote down the answer.
Please read it.
In an experiment to make hydrogen peroxide, a chemist mixes 20.0 grams of hydrogen with 20.0 grams of oxygen. She finds that 21.3 grams of hydrogen peroxide are produced. In addition, there is a lot of hydrogen left over at the end of the experiment. How many grams of hydrogen should have been added to the 20.0 grams of oxygen so that there would be no leftovers at the end of the experiment?
Well, it says that there's leftover oxygen, right?
Mm-hmm.
From that, we can assume that all the hydrogen is used up.
Yeah.
So we can see if all the hydrogen is used up.
Actually, it says there's lots of hydrogen left over.
Is that what it says?
Yeah.
The opposite way around. Okay, then all the oxygen is used up. If all the oxygen is used up, then how much hydrogen is used altogether?
20.0.
No. That's how much she used, but there's leftover hydrogen.
Oh.
She only used 1.3 grams of hydrogen.
Well, how much is left over is it's 18.7 grams.
Okay, but the question is, how many grams of hydrogen should have been added to the 20.0 grams of oxygen so that there would be no leftovers at the end of the experiment? You can do this kind of in two ways. I mean, I'm looking at it and I'm saying, well, obviously 1.3 grams. That's how much of hydrogen she should add because she used up 20 and it's 21.3. But what we really are supposed to do is we add these two up. We get 40.0. We subtract 21.3. We find out that 18.7 grams are not used of the hydrogen, and then we subtract that from the amount that was used, and then this was the leftover, and 1.3 was actually used. And so that is how, so you can do it either way, right? It's the same answer. It's 1.3 grams should have been added to have no leftovers.
Right.
Okay? And we're going to do number 5 right now.
In making calcium nitride, 100.0 grams of calcium plus 100 grams of nitrogen makes 152.5 grams of product along with... It is
100.0 grams, right, of nitrogen?
Yes.
Thank you.
Makes 152.5 grams of product along with some leftover nitrogen. How much nitrogen and calcium should be added together in order to make 1.0 kilograms of calcium nitride without any leftovers?
All right, so how much is used altogether in our ingredients, as it were? Hello? 200 grams are added. All right, total. We get 152.5 grams of actual product, right? So how much is left over?
Well, that's 40.
All of the calcium is used, right? So there's only nitrogen left over. Yeah, so we're going to subtract, right? So 200.0 grams, okay, minus the actual product will tell us how much was not used.
It was 47.5.
Yeah. Okay, so 47.5 grams of nitrogen is not used, right? So how much nitrogen is used? Of the 100 grams, only
52.5 grams.
Yeah, 52.5 grams is actually used. right?
Yeah.
Okay, so if that's the case, then the scientists used 100 grams of calcium and 52.5 grams of nitrogen to make 152 grams of the calcium, what was it called? Calcium nitride, whatever the product is. Okay, so now we need to find the conversion factor for 152.5 grams to 1.0 kilograms. Well, 1.0 kilograms times 1,000 grams per 1 kilogram is going to give us, I'm going to keep it in scientific notation, 1.0 times 10 to the third grams, right?
Yeah.
So we want to find out what we need to multiply 152.5 grams by times X, I'm going to call it some conversion factor, to get 1.0 times 10 to the third grams. So in order to get X, I need to divide by, my units will cancel, which is good because I only want a number for my conversion factor, not something with units. Okay, so 1,000 divided by 152.5. So the conversion factor is 6.55737. Okay, so this has two significant digits. This has 4. I only want to have 2. So what am I going to record as my conversion factor, Smarty? I only want to have 2 units.
Right.
2 digits.
You want 6.6.
That's the one.
Sorry,
Okay, but I'm not done yet. Now I have to go back and I have to find out how much of these two products I need. So I'm going to multiply 100.0 grams of calcium times this conversion, 6.6. It's basically going to give me 6. So here I have 2, 1, 2, 3, 4. I only want 2, 6.6 times 10 to the 2, really, grams of calcium. And for the nitrogen, I used 52.5 grams, and I want to multiply it by 6.6. $52.5 times 6.6 gives me 346.5. What do I want to say for that, Martin? Because I don't want to say, I only want how many?
2.
2. So I'm going to say
3.5 times 10.
Times 10 to the 2 grams of, what is this, nitrogen.
Yeah.
Okay, so we want 3.5 times 10 to the 2 grams of nitrogen and 6.6 times 10 to the 2 grams of calcium in order to make 1,000 grams of this mystery substance. Okay, we're going to keep going. Power on. Read number 6 for us.
What is the chemical formula of a molecule? Should I wait for it?
No, go ahead. Keep going.
It's made up of 3 carbon atoms, 6 hydrogen atoms, 2 chlorine atoms, and 1 oxygen atom.
Okay, so we have to know the scientific symbols for those elements. So carbon is C. How many were there?
3.
3. How about hydrogen?
That's H.
H.
That's Cl for chlorine.
So I'm going to say C3H6.
Cl2.
Cl2.
And 1.
O.
And O.
And we don't use a 1.
Because it's all. That's what it's considered.
It confuses. It looks funny. All right, number 8. No, that was 6. Excuse me.
How many total atoms are in one molecule of C12H24O10S2?
Okay, so we add up these numbers. 12 plus 24 is 36. Plus 10 is 46. Plus 2 is 48 atoms. Okay, number 8.
Which of the following molecules are covalent? A. SO3. B. P2H6. C. CaSO4. D. D, KF.
Okay. So in order to decide if they're covalent or ionic, we need to know if they, what, Martin?
If they
contain a metal. Okay, so SO3 is covalent. That's sulfur and oxygen.
No. Yep, that's covalent.
So this is, so the question is it covalent or not?
It's covalent.
Check. All right, how about P2H6?
Let's see. P is covalent. Let's see. H is also covalent. So the covalent.
Well, you say P is a non-metal. It's phosphorus.
Yeah.
And H is hydrogen. Covalent. Bing. How about CaSO4?
Let's see. Okay, Ca is a metal. So we don't even need to do the rest.
That's going to be ionic. How about Kf?
Kf. Let's take a look at that K. I got a good
K is potassium.
K is a metal.
K is a metal.
Not covalent. Name the compounds in problems 8A, 8B, and 8D.
Yes. C contains this, which is called sulfate. So we're not going to worry about it. You'll learn how to identify that later.
So the first one is sodium trioxide.
Okay, so this one is a covalent compound, so we have to use the covalent nomenclature rules. So you are correct. One. You say sulfur trioxide. If you don't know why we're calling it that, please ask. I will be happy to tell you. Letter B.
That's potassium hexahydride.
It's not potassium. Potassium is K, so we're naming letter B.
So that's
So this is a covalent, so we have to use the nomenclature. So there's two atoms in of phosphorus, right?
Okay, it's phosphorus.
So if there's two atoms of phosphorus,
diphosphorus hexahydride.
We have to say diphosphorus. And what is the?
This last one is ionic, so we get so we have to use the boron.
And 6 is hexahydride. Okay, and we're skipping C because we don't know how to name this yet. It's outside the rules.
And D is boring because it's just.
D is an ionic compound, and so rather than worrying about the prefixes, we're just going to name the elements, and that is potassium.
Potassium. I don't remember what F is.
Well, look it up.
I am doing so.
Right there in your chart.
Krypton, is that? What's an actual one? Jeez,
fluorine. It's fluorine,
okay.
So you're going to call it?
Potassium fluorine.
No, you're going to call it?
Potassium fluoride?
Yeah, don't you call it potassium fluoride?
I guess.
Yeah.
Krypton, jeez.
The next atom should have an "ide" for the ending. That's what it says on page 90, rule number 2 for ionic compounds.
10.
Number 10.
What are the chemical formulas for the following compounds? Geez, man, chemical names get pretty awesome. Tetranitrogen hexahydride.
Okay, what's?
Okay, so that's
tetranitrogen. I'm gonna write an N for nitrogen.
N4H6.
That's right. Hexa.
Okay, nitrogen monoxide. This one's boring. That's just NO.
No.
Okay, we done.
Oh. Hey, thanks, Balloon Man. You are a cool cat. Oh wait, you're not a cool cat. You're a cool dog.
Yeah, dog.
Oof.